Okay, so example 7.7 is conceptual, and it kind of makes it a little bit confusing when you look at the math they do. Let's just talk about it. They're asking if someone is to push this mass, and the problem is a refrigerator or something, on a dolly. The guy is pulling the dolly back, ding, ding, and trying to push that up the hill. Um, What we're fighting against, though, is this mass that's on an incline. We're fighting against its weight, mg. So the work we're doing is the work of a weight, or the work due to weight. Now let's take a look at that. They're asking if the ramp is longer, would that make it less work? Or what if there's no ramp at all? I posed that question myself. So if the ramp is longer, it's not straight. Let's draw a longer ramp. Okay, it could go all the way out to there. Is that going to help? Well, let's take a look at this. The work due to a weight is equal to the weight itself, the force, right, times the displacement. In this case, delta y, and the delta y is equal to some h. If we were to make this angle less steep, yes, it would be easier to push up it. If we were to take the ramp away completely, we would have to lift the entire mass, the whole component of the weight up to the truck. But does it do less work? That's the question. Does any scenario cause us to do less work? And it's no. All that matters is the displacement in the direction of the force that we're dealing with. In this case, it's just the force of gravity, and that's mg, and it's acting some distance h. If I change the length of the ramp, that does not change this length or the distance h at all. If I got rid of the ramp and had to lift this block directly up into the back of the truck, I would still have to do the same amount of work. In fact, I can take a path like this and it turns out that delta H is still the same all the way from ground level to the bed of the truck. We get the same exact H value. So when we're dealing with the work due to a gravitational force or a mass having a gravity or a weight to it, all that matters is the displacement in the direction of that force. And we get the minus sign because the displacement is going up and the force is acting downwards. So, no, none of these scenarios make you do less work. Yes, the ramp makes it easier, but you still have to do the same amount of work. You still use the same amount of energy. If you were to lengthen the ramp all the way out to here, it's going to be significantly easier, right? If you've ever done any hiking or anything, the grade of the trail makes a big difference. Something very, very, very steep gets very tiring, where you make an incline a lot more shallow with some different angle theta, and it essentially feels easier to go up it. But to gain the height h in this case, it's still going to take the same amount of work, and that's independent of the path. So that's why I drew this squiggly. We could have gone down first and then brought it up and over like that and still done the same amount of work. And you can integrate, if the work is equal to the integral of f dotted into dr, or you can integrate across this path, is what I'm trying to say. And you can prove that. It doesn't matter what path that you're going along. We're going to see that is because this is the weight is a conservative force? And I'll go more over that too and how we can identify conservative forces. But a good example of what is not conservative and why we haven't really been working with it so much yet is friction. Friction turns into heat. Friction turns into light, sound, all different types of energy, and we cannot turn that back into what we call mechanical energy. I can lift this object up the ramp and then let go and turn it right back into mechanical energy if I want. I can use all of that energy, and we'll see I can turn it all into 1/2 mv squared, or the kinetic energy, right? I defined that for you in the last video. When we use the conservation energy, that's exactly what we'll be doing. But one of the things we cannot include in the conservation energy, unless you kind of use a trick I show you, will be friction. We can remove the amount of energy lost from the system, and I'll show you some tricks on how to do that, but in general, the conservation of energy is not going to include friction in it. Really important, note that this is independent of the path. We were able to do the same amount of work. I could have literally gone up 10 miles and then brought it back down to the back of the bed and still done the same amount of work. Because even though I might have done a bunch of work getting up to the 10-mile high point, I get a lot of that back as I bring it back down. And you'll see that when we start working with conservation energy, when some mgh turns into some 1/2 mv squared, things like that. All that matters is position 1 and 2, speed 1 and 2 could be the velocity, but we're really just dealing with speeds. So the speed 1 and 2, and whatever force is applied from 1 to 2. There may be a bunch of forces, so let's call that the summation of the forces. Yeah, I didn't want to overlook this, and if you look at the math in the textbook, it kind of points you in a weird direction, but I think we can make a lesson out of it, so I did it.